Hello everyone, my name is Rtkhosa. I'm here to share with you the simplest topic in mathematics called mathematical logics. So here we're going to focus on statement assigned to letters. So mathematical logics are all about conjunction, disjunction, and negation of statement. So let's start. As I said, logic is all about reasoning. So in this case, letters are assigned to statement. For example, we can assign letter P to a statement called John loves his mother. So the basic concept in mathematical logic, we have the implicit statement. This one is also known as the conditional statement. So this one is an if-then statement. So P implies Q. So what it means is that P can be represented by John loves his mother, and Q can be represented by he is a good boy. So the whole statement P imply Q will state that if John loves his mother, then he is a good boy. We also have the biconditional statement. So this one is two-sided. P can imply Q and also Q can imply P. That's what I mean about the word two-sided. So which means in this case, if P is true, Q has to be true. If Q is false, P has to be false. So vice versa. And again, we look at the negation of a statement. The negation of the statement is the opposite of the statement. It's represented by this sign, as you can see here. So this sign, negation of P, means the opposite. So remember, your P was John loves his mother, but now we negate that, we write the opposite. We contradict what P says. So it is that John does not love his mother. So we have also combined and disjoint statement. So let's start by disjunction, the or. It's also known as the union. So it connects two or more disjoint, common or unrelated statement together. So we can take it from previously. You can add any two numbers, 3 plus 5, or 3 plus 2 plus 3, it's 5. These two numbers are disjoint, but it will give you this number. So we are connecting them. An example, you can have a bridge. Remember, if this is the bridge, it means this is a land and this is another land. So this bridge connects two disjoint lands. So that's what it means about the union. So they don't have to be common. That's why I said they can either be common or unrelated. But when we talk about the conjunction, they must be common, both sides. So it combines two statements into one common statement, as you can see here. So we also have equivalent statements. Okay, equivalent means equal or same statement. It's represented by this 3 equal sign. You can see it. So we are, for example, as when we said P implies Q, is equivalent to not P or Q. So the negation of P implies Q is equivalent to P intersect not Q by De Morgan's law. We'll discuss that. So let's focus on basic laws. Under basic laws, we assume we have 3 statements, P, Q, and R. You can assign any letters for the statement. You can assign letter A, letter B, letter C. I just chose P, Q, and R. So hopefully you understand. So we have idempotent law. Under this law, it's where we are going to say John loves his mother or John loves his mother. So the solution will be John loves his mother. So it's equivalent to P. So this one is Q or R. Intersect Q or R is still Q on R. Idempotent, same thing, is intersecting itself. We get that thing. So we also have the second one called the commutative law. So from, you know that X plus Y is the same as y plus x, and this is commutative law from numbers. So the same thing I did here with 2 plus 3, I can write it as 3 plus 2. Doesn't change anything. So that's how commutative law works. So P or R, it can be R or P. Same thing, R intersect Q can be also Q intersect R. Then we have associative law. So associative law, we are associating the brackets. Do you see these brackets? When we come this side, we just move the brackets. We associated them. So even on this case, you can see intersection. So we are allowed to write this way. We can associate the brackets. That's how it means. So most interesting, distributive law. P or R intersect Q. So we can distribute this one. Let me elaborate it. It's more like this. I'm having x plus y multiplied by z. So I'm distributing. By FOIL, you know, it's this times this, it's xz, plus this times this, it's yz. So if you can check here, it's more like as I wrote here, that we can take conjunction as multiplication, we can take disjunction as addition. So representing this example, you can see you're having x and y and z. For the three statement, we can write P. For this, we say union Q, then intersect R. So the solution will be x multiplied by z, which will be your statement P intersect R. You can see union Q intersect R. Hopefully you understand what's going on. That's all about this. The last one is, not last, we have complementation law. We are taking the negation of the negation. Remember, the negation of P is that John does not love his mother. If we are negating again, John does not love his mother, we'll end up having John loves his mother. That's why a negation of a negation is just that statement. So, and also, I have shown you this on the equivalent statement, that the negation of this, which is the same as this, is the same as this. So this is mostly explained by the following law, De Morgan's law. So this law is that the intersection and the union, the exchange, the negation of intersection is the union. The negation of the union is intersection. So if we negate P or Q, we have not P intersect not Q. Or we negate P intersect Q, we'll have equivalent to not P union not Q. So let's just try to apply. Can you see this example? Not P or R intersect Q is equivalent to not P intersect not into R intersect Q. So can you see by De Morgan's what we did? We introduced the negation of this and the negation of this whole thing. That's De Morgan's. And you see that this union changed to intersection. And here you proceed for this part, you can also apply De Morgan's. It comes here by De Morgan's law. So this one is this way as you see it. So we can see it's by distributive law as I've shown you. We can say this as you can see, intersect this. The same thing, this intersect this, but don't forget the union. Now the distributive as I presented here, it works, so you understand. So you'll try and solve this example as an exercise. You can see it, look at it carefully. You can try to copy it in few seconds, then yeah. Welcome again, still Rtkhosa here. We're proceeding with the last video on mathematical logics. We last stopped in the example where we applying the laws. If I can rephrase, we're doing this one. I gave you an exercise. So now let's consider the truth table. So whatever we discussed before, they're very much important on the truth table. So that we're going to focus on right now is the truth value first. Truth value, the logical value of a statement. It can either be true or false. So a true statement is called a tautology, also called a valid statement. And also a false statement is contradiction. It's also an invalid statement. You'll understand this more on the arguments of statement. What do I mean? So, but right now, let's focus on those three concepts which we're focusing on. Implicit statement. Remember a statement P imply Q. The truth value of this statement, it depends on Q regardless of the truth value of P. So what I mean with this, I say P imply Q will always be true statement as long as Q is true, regardless of the truth value of P. P can either be false or true. Q, as long as Q is true, this statement will be true. The explanation for this implication is that a false statement can imply a true statement. A true statement can imply a true statement. A false statement can imply a false statement. But a true statement cannot imply a false statement. You know this in a normal talking way, or a lie can turn up becoming a truth. You get up, but a truth cannot be a lie. So you know what is going on. For example, an opinion can become a fact, but a fact cannot become an opinion. Hopefully you understand about that. So now we look at the combined statement and the disjoint statement. The disjoint statement, this statement is true if one of the statements is true or both are true. As long as P or Q can be true, even if this one is false, this one is true, this statement will be true. That's how the union works. It's all either one of them or both. So you must understand. As I said, it's either one of them or both. So we also have the combined statement. P intersect Q. P intersect Q is true if both are true. Otherwise, the result will be false. What do I mean about this statement? If your P is true and your Q is false, then this statement will be false. That's what I mean. I say the result will be false. So they have to be both true for this to support the combined. So they have to have something in common. In mathematical arguments, we'll understand more about this. Don't worry. And also the existential and universal quantifier. We're still going there. So we are having truth table now. How can we construct a truth table? I know most of students are having challenges when it comes to this concept because you think like you're creating the columns and the rows. No, there is a formula. The number of rows is given by 2 to the n, where n is the number of statement. Remember, we assign statements, number of statements. We assign statements to letters. So as we chose before, we said last statement PQR B statement. So I'm going to use truth table to prove whatever law we've discussed before is true. So let's start with the implicit, or these two are equivalent. But before we go there, you have to understand this. Let me just erase this. It was unnecessary. What I wanted to say about this is that for you to determine on each column per your given statement, you have to take from the total number of rows, you divide by 2, then you take from that other result, you divide by 2. Actually, this one is more explainable in examples. So let me just show an example, i.e. example number 1. P imply Q. There are only 2 statements here, P and Q, with equivalent to not P or Q. So R is given by 2 to the power 2, which is equals to 4. So this is our number of rows. Let's count. 1, 2, 3, 4. Row, this is a row, this is a row. There are 4 rows. So to see in rows, in columns, in each and every column, for these two, they must share equal chance. We must have equal chance. So we see that by saying we take 4 divided by 2, we get 2. It means the first one we start by 2 true, 2 false. We take 2, we divide by 2, we get 1. That's why you have true, false, true, false. Hopefully you understand. Now is the knowledge of what we learned. What is the negation of a statement? The negation of a true statement is a false statement. That's why you have T, the negation of P, where is T is false. Where it's false is T. Hopefully you understand the implication. We go back to these 3 conditions. We say a true value, if a true can imply a true. We said yes, it's true. A true can imply a false, And we know that a true cannot imply a false. That's why we wrote it's false. So a false can imply a true. Yes, it's true. A false can imply a false. It's true because it's written in these 3 conditions. So we proceed. Now we come to the union. Not P union Q. There we have what? The union of these 2. So this union, this is true. False union, false, it's a false. True union, true, is true. False union, true, is true. The last one is the conclusion. The conclusion, we look at each row if these 2 match. If what we said they are equivalent, they are truth. They match, yes, they match. So that's why we wrote true, 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 they match. So it's a valid statement, which is a tautology, as I explained. So for me to know the number of columns depends on the number of on what you are asked to prove. First thing first, we're supposed to prove this. The reason I introduced not P because we have to negate P first, then we can also have P imply Q itself, then we also have not P union not Q. So you can see what's going on. That's how it is. So yourself go and try this one. The negation of P imply Q, which is P intersect not Q. So in this case, it means that you're going to have for P and Q, they will be the same. The only difference now is that you'll have to have P imply Q is also the same. You'll also have to have the negation of it. So you also have to have the negation of Q. You also have to have P intersect not Q. Then you're going to compare the column for this and the column for this. If the outcome values, are they matching? If they are matching, you conclude with your true value. You'll find that they are matching because this one is already a proven law. You know, like in mathematics, a definition is an if and only if statement. So they are already matching. Equivalence is more like if and only if conditional, but I cannot take it as that, but equivalence means equal. So proceeding to example number 2, now we have 3 statements, P, Q, and R. That's why you see now your small r number of rows is 2 to the power 3, which is 8. So which means how many truths are going to go with P first and false? There will be 4, 4. How many truths are going to go with Q and false? It will be 4 divided by 2, which is 2, 2. For R, it will be 1, 1. That's why you see here, for P, I have first 4 truths, last 4 false. On Q, I have 2 true, 2 false, 2 true, 2 false. That's how we do it. It's an easy thing to apply. Then on R, I have true, false, true, false, true, false, true, false. So now it's a matter of what you'll understand why I'm having these columns. I'm having these columns. Let's start. We need first P or R. I started with it. P or R, you can see true or true is true. True or true. Oh, I mean P and R. True or true is true. True or false is true. True or true is true. True or false is true. You can see false or false is false. Let me not be fast. False and true is true. False and or false is false. I'm using or now. It's not and. So don't be confused. I'm still at P or R. So these are the results of P or R. You understand? If you understand what do I mean about for P or R to be true, it's either P is true or R is true or both are true. But if both are false, the result will be false. That I mean. So you will understand. So now let's check this one now. P intersect Q. So you know it's only true if both are true. So both are true is true. Here both are true is true. The rest, it doesn't matter true or false, false or false, false or true. That's why you see false, because they don't match. Thank you. So same thing here, R and Q. This and true is true. You see, false and true. R is false and Q is true. True and false, you can say it will become false. So it will only be true at this part where they are both true, the rest are false. Then we are going to, I was explaining this for the, this one is for R, it's not this one actually, don't be confused. R and Q is this one. So now let's go to P union R intersect Q. So we take which one here? On this one, P union R, we consider this, then we intersect with this. We are going to take true and true, you see, we get a true. You can see what's going on. True and true, we get a true. But you can see here we have a false and a false, that's why it's a false, false, false. You know how intersection works. True and true is true, the rest are false because they are not, these two are not correlated, so different outcomes. For intersection, same outcomes, it should be true and true, we get true. Else, it's false, as I said. So we come to the last one now. We take the union of P intersect Q and R intersect Q, the union of the two. So you can see here we're talking about two statements. Which are they? These two statements. The union of these two statements. The union of this is true or true is true. True or false is true. False or false is false. You can see. False or false is false. You can see false or true is true. The rest, because it's false or false, are false. So let's see. This match, 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 this match. So therefore the result is this one. So you can prove anything. So if you want to see better understand this thing, it's an easy thing. You just have to do more exercise on this one. So let me just show you from the previous class we had. Can you try and go and prove for associative law? Go and try and prove what we didn't prove. Here we're proving the intersection of Q. Now can you please try and go and prove this? We're going to prove that P or R, on the distributive, let's see, not associative, let's start going to try and prove this. P or R intersect Q. You must prove this is the same as this. Go and try and prove this. I made a mistake on that one. This is your exercise. You can see it. Must look at it carefully. Go and try and prove it. Thank you for watching. You are welcome. Keep on subscribing.